in previous lecture, we learn about eigenvalues and eigenvectors and see some properties and these properties of eigenvalues and eigenvectors. So here I explain these properties. Or next, some use and applications of eigenvalues and eigenvectors in our real life or real world problem. Okay, so now we start. Here, if we have eigenvalues lambda 1, lambda 2, so on lambda n of n cross n matrix, square matrix, and the important results. Sum of all diagonal entries of these is trace of A. Okay, and determinant of A from so determinant of A. For example, I explain this topic as with the help of one example. For example, you have this matrix 1, 2, 3, 4, 0, 5, and 6, 7, 0. So you have to, when you have to determine its determinant, then you have to apply proper rules. But if you have, you know its eigenvalues, then it is very easy to find its determinant, because if you have its two eigenvalues, suppose let's suppose here lambda 1 is equal to 2 and lambda 2 is equal to 3, and you have to multiply with lambda 1 and lambda 2. So multiplying with lambda 1 and lambda 2, we have 6, and 6 is eigen, its determinant. So from eigenvalues, we can make determinant results about determinant, or we can find determinant very easily. And here lambda 1, lambda 2, so on lambda n is our general case in case of n eigenvalues, okay, or nth degree polynomial degree. Spectral radius of A is the raw A, and it is the maximum of all these eigenvalues. These are the absolute values. Mean if we have -3, then you have to find its absolute value first, and absolute of value of -3 is 3. So all the absolute values, find all the absolute value of eigenvalues, then its maximum is the spectral radius. So spectral radius always less than the norm of the matrix, and this is the distinct corresponding eigenvectors, then they are linearly independent. Now we see some other properties and some properties of eigenvalues. Since eigenvalues of a matrix, for example, we have the matrix A. Okay, in the previous slides we studied general concepts about its spectrum, its determinant, and its determinant or spectral radius or trace. Here we want to show all these steps with the help of one example, or we take one example, put all these previous concepts or points onto it and formulas onto it, and show how we calculate all these terms. Okay, so eigenvalues of the matrix, here in the previous slides, we, as you know, we calculate eigenvalues are 1, 3, and 6. So here we have 3 eigenvalues, lambda is equal to 1, lambda is equal to 3, and lambda is equal to 6. So spectrum of A is equal to 1, 3, 6. Spectrum of A is the set, and all these set of all these eigenvalues in this spectrum. So spectrum of A is equal to 1, 3, 6, and trace of A, sum of all the eigenvalues of A. Eigenvalues are 1, 3, and 6. So 1 plus 3, 1 plus 6 is equal to 10. And determinant of A, multiplication of all these eigenvalues as we determined in our previous formula, previous slide formula. So lambda 1 multiplied by lambda 2 and multiplied by lambda 3. Here what is lambda 1? Lambda 1 is our first eigenvalue, and it is 1. Lambda 2 is our second eigenvalue, and it is 2. Lambda 3 is our third eigenvalue, and it is 6. So determinant of A is equal to 1 multiplied by 3 and multiplied by 6 is equal to 18. spectral radius of A. Spectral radius of A is equal to maximum of all the absolute values of eigenvalues. So you know absolute value of a positive number is positive. So one absolute value of 1 is 1. Absolute value of 3 is 3. Absolute value of 6 is 6. And maximum of all these absolute values is equal to 6. You know the number which is greater than or maximum of all these values is 6. So maximum of all these values is 6. So spectral radius of A is equal to 6. So next we see real life applications of eigenvalues and eigenvectors. How we use eigenvalues and eigenvectors in our real life and real world problem. So Google page rank. Google page rank is very important and very vast use of the eigenvalues and eigenvectors. For example, you search some topic on Google and you see some pages are related to our search, and most related to our search are in top of our search list. So these the Google page rank decide which page appear to our in our priority one, and then which link or which PDF file or which page appear or website appear in our second rank and one rank. So Google's page rank is totally depend on eigenvalues and eigenvectors. Okay. So next, Google's extraordinary success as a search engine was due to their clever use of eigenvalues and eigenvectors. You see, when you search Google and you type about formula about the matrix, then you exactly found all the pages which includes formula about the matrices. And you see, it is never happened you search about matrix and the Google give you result about any other topics. So which topic you search, your results also include that topics, and very matching pages or PDF files and other links are appear on our top list of search. So that's why this is why this is happen. This is the clever use of eigenvalues and eigenvectors. They use eigenvalues and eigenvector Google use in its Google page rank and show the searcher priority material, and which material most match to searcher keywords. Okay. So next, Google's method for delivering the most relevant results for our search queries, page rank technique. Google's methods for delivering the most relevant result for our search queries use page rank technique. Okay. So here are some more examples or applications of eigenvalues and eigenvectors in our real life. Let's assume the web contains 6 pages only. Now we give the example of how the Google use the eigenvalues and eigenvectors in searching and page rank. So let's assume the web contains 6 pages only. The other of page 1 thinks pages 2, 4, 5 and 6 have good content and links to them. And the other of page 1 thinks the other 2, 4 and 5 number pages have good content related to their topic. So related to his topic, and he links to them. The other of page 2 only likes pages 3 and 4. So he links from these pages to them. The links between these and the other pages in this sample web are summarized in this diagram. Now we show one diagram, and we this is the diagram. For example, in this diagram, you see these are our 6 pages. Okay, the page, this is the owner of or other of page 1. Okay, the page 1 like 2, other of page 1 like pages 2, 4, 5 and 6. So he linked 1 with 2, 1 with 4, 1 with 5 and 1 with 6. These are our arrows show linked pages with the other pages. Okay, the other of page 2 only likes page 3 and 4. You see here other of page 2, and page 2 only like 3 and 4. So arrow goes from 2 to 3, arrow goes from 2 to 4. Here you see other of 2 does not like page 5. So here arrow does not go to 3 to 4. Similarly, the arrow does not go to 2 to 6. So other of page 2 likes these. So he linked these pages. The links between these and other pages in the simple web are summarized, or these are summarized. Here you see 6 goes to 5, mean other of the page 6 like 5. And 5 goes to 4, mean other of the page 5 goes to 4. And also 5 goes to 1, mean other of the page 5 likes 1, 4. And next, real life applications of eigenvalues and eigenvectors. Their task was to find the most important page for a particular search query as indicated by the writers of all pages. Or for example, if anyone linked to page 1 and it was the only one that had 5 incoming links, then it would be easy. Page 1 would be returned to the top of our search result. What they are asking here, their task was to find the most important page particular to our search query. For example, we search about matrices, and the page which have most relevant data about our search or topic matrices then is indicated by the writers of all 6 pages. If everyone linked to page 1 and it was the only one that had 5 incoming links, then it would be easy. Page 1 would be returned at the top of our search. If many others linked page 1, okay, all the others linked page 1, then it is more chances to appear page 1 in our search list. So however, we can see some pages in our web are not regarded as important because some of the pages are not important, but when instead of unimportance, we see it in our search list. So that's why this is the linkage. If the authors of other pages and link the right pages to their page, or so we see more accurate results related to our search queries or our keywords. So one thing is more important. You have to choose right keywords for searching. If you want to know about definition of matrix and you just write about more something with instead of writing definition of matrix, you use other keyword, then maybe you find less accurate data about the matrix. So use important keywords and famous keywords for searching. So that's why top rated or our priority 1 page must we find. For example, page 3 has only 1 income link. In our previous slide, you notice that page 3 just has 1 income link. So page 3, for in this diagram you see page 3 has just 1 incoming link. It is 2 to 3, and no other all others of the other pages link these page 3 from 1. So there are less chances of page 3 to appear in our research list. So the page bank regarded the pages with many incoming links as more important than other pages. For 6 page web, we can form a link matrix representing the relative importance of the links in and out of each page. And considering the page 1, it has 4 outgoing links to page 2, 4, and 5, and 6. And so in the first column of our link matrix A, we place value 1/4 in each of row 2, 4, 5, and 6. Since each link is would 1/4 of all the outgoing links. So see the rest of the rows in column 1 and column 1 have value 0, and since page 1 does not link to any of them. Now we translate these lines. In our first point, we say page bank regarded the pages with many incoming links as more important than other pages. So the page rank of incoming links are more important. In which page whose incoming links are greater than the other pages, then the greater number of incoming link page is in our top priority list of search. So in second point, we see page for the 6th page where we can form a link matrix. We link a matrix representing the relative importance of the links in and out of each page. So in a matrix, we write the importance, how many links are from coming for page 1, how many coming links are for page 2 and 3 and so on 6. So we write all these their importance in a one matrix form or consisting page 1. It has, for example, you see page 1, it has 4 outgoing links, and page 4 outgoing has 4 outgoing links, and it is mapped on 2, 4, 5 and 6. And so in the first column of our link matrix A, now from our these calculations or from this data, we have to a matrix. We have to write a matrix and name this matrix as a links matrix A. This link matrix, we write all the outgoing or incoming links. For example, in our page 1, we have 4 outgoing links. So in our link matrix A, we place 1 by 4 in each of row 2, 4, 5 and 6. Since each link is 1/4 of all the outgoing links. So total are 4. So we write row 2 for page 2, row 4 for page 4 and row 5 for page 5. So in all these rows, we have to write 1/4 as outgoing links. The rest of the rows in the column 1 have 0 values because without 2, 4 and 5, the page 1 has no outgoing link. So all other values of other rows are 0. Since page 1 does not link to any of them, in this we just go through outgoing links. Incoming links of page 1, here we neglect outgoing links of page 1. Meanwhile, page 2 has only 2 outgoing links to page 3 and page 4. So in the second column, we place value 1/2 in row 3 and 4. So page 3 is for row 3 and row 4 is for page 4. So in the second column, we write 1/2 because why we write 1/2? 1/2 means our total outgoing links are 2. So for what page? For page 3. So we can see it with a help of diagram. You see, one has 3 outgoing links. Okay, so page 3 has 1 outgoing links, and it goes to 5. Or page 4 has 2, 1 and 1 outgoing link. Or so we write it in a column 3 and 4. Okay, so this is our matrix, and we make this matrix, and this is the linked matrix. Okay, we name this matrix a linked matrix, and you see here I write in row, this is our first row and 5th column. So we linked page 1 with 5th row with 5th page. So in first row, the 5th entry, we write 1/2. Here 1/4, 1/2. These are the linked matrix, and we make it with the help of these points. And we explain better in we explained very deeply or in more detail. So next we see this. And so we first of all, our first step is to make linked matrix. Then we have to find all the eigenvalues and eigenvectors of this linked matrix. So this is our characteristic equation of our linked matrix, and this bar show its determinant. For example, determinant of A minus lambda I. Here we have to find the determinant of our characteristic polynomial minus lambda and 0, 0. These are all obtained from A minus lambda I. Here what is I? I is our identity matrix of that order of order of A, of as same as the order of A. So we calculate this is very large matrix, and we can calculate in modern era. We calculate all the matrices, transpose, inverse with the help of Google calculator. calculator or our own calculator. So we calculate this determinant with the help of a calculator because it is a time taken task, and in this matrix we have more concern about its application and seeing its eigenvalues, not the calculations. Calculations are robotics, so we take help of machine and computer or calculator for determining its determinant. So after determining the determinant of link matrix A, you see which are these values, these and these. So these are the eigenvalues. Here, how many eigenvalues? It has 4 eigenvalues, in which one eigenvalue is complex. Complex means this. Here we have iota, and iota shows complex numbers, and we learn about that eigenvalues can be a real number, can be a complex number, or combination of real and complex. So here we have point minus 0.72031, it is real number, and minus 0.13985 plus minus 0.39240 iota, and this is the complex number eigenvalue, and next we have 0 and 1. So we have total 4 eigenvalues, and now we have to find the eigenvectors corresponding to that eigenvalue. So we always take lambda is equal to 1. First of all, we take lambda is equal to 1. Here we find all the eigenvectors, and here we have 4 eigenvalues. So we definitely have 4 eigenvectors. First of all, I take eigenvalue 1 as a lambda 1, and we find v1 as the eigenvector. So as fifth component is for the page 5, so it has highest page rank of 8 of the above vector. You find v1, and you see all the entries of these v1. v1 is 1, 2, 3, 4 and 5, and fifth entries of this eigenvector is 5. So from this we conclude that so it has the highest page rank of 8 in the above vector. We conclude it the most important, and it will be appear at the top of our search results. Our research results, we conclude which element of that vector has highest value. So the you see number of rows is equal to number of pages. So here is here 8 is fifth value, so page 5th has higher rank, and then other values are show on the top of our list. Okay, next we see some practice questions, and here we have one question: find the eigenvalues and eigenvectors of that matrix A. And here, for the sake of satisfaction, I write answer here, and we have to calculate and match our answer, either or this is our right answer or not. I just write questions here and then answer here, and then you have to calculate this by own. This is the assignment, and let's see previous assignment. Find out one real life application of eigenvalues and eigenvectors. You think about it. I give one real life application of eigenvalue and eigenvector is Google page rank, or you see how the how deeply I explain this, and so similarly in this way you have to find one other real life application of eigenvalues and eigenvectors. Our second practice questions are these, and we have to write eigenvalues and eigenvectors of this matrix. So what are the steps you have to for finding the eigenvalues and eigenvector for this matrix? So first of all, you have to write characteristic equation. So what is our characteristic equation? We have, first of all, you see this is the 3 cross 3 matrix, 3 by 3 matrix, square matrix. So you have to write identity matrix as a 3 by 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. This is our identity matrix. Our next step is A minus identity matrix, then multiply it with X. So we have write this. This is our characteristic equation, and then we have to find its determinant. So a minus lambda x mean if we multiply, sorry, here we have lambda I. Here we write lambda I. A minus lambda I and its determinant is equal to 0. This is our homogeneous system, and here I write we have to find the value lambda, and then putting the value of lambda we find the Gauss eigenvector with the help of Gauss elimination method, or you have you can choose other methods, Gauss elimination method, Gauss Seidel method, and some other methods for solving homogeneous linear system of equations. So here we write a minus lambda I, and a over our a is minus 7. Okay, so minus 7 plus lambda, all the entries are same, 2 and minus 3. Then we have write, okay, we write in next slide. We write it in next page over here. So what is our a characteristic equation here? So a minus 7 plus lambda. The entries are changing. Here we have minus 4 plus lambda, and here we have minus 5 plus lambda. All the other entries of that matrix remain same. We just make changes in them because our identity matrix affects these elements. Okay, so after finding this, you have to find its determinant, and from determinant you will reach at lambda 1, and which is 0, lambda 2 which is 8, and lambda 3 which is minus 8. So when you put lambda 1 is equal to 0 and solve it by Gauss elimination method, you will find V1 is equal to this. And when you put lambda 2 eigenvalue in your homogeneous system, make augmented matrix and solve it by Gauss elimination method, then you have you will reach at V2, and it is second eigenvector. When you read about V3, put the eigenvalue V3 is equal to minus 8 in your homogeneous augmented matrix, then solve it by Gauss elimination method, and you will find V3, and V3 is this. So this second question is same as above, just values change, procedure and steps are all same. So here from this method we can find the eigenvalues and eigenvector. So what we learn from today's lecture? Here we learn first of all what is eigenvalue, then eigenvector, and then we learn about how, in the main topic of our of this lecture is real life applications, and how, and you see Google page rank, and also learn about link matrix, and with link matrix, and how we form link matrix, then how we solve these link matrix and find eigenvalues and eigenvectors, and with the help of this link matrix how we calculate the our results and conclude the results of page rank, and we see the top which page on our top research or top search results. So then we have to find some other real life applications and of eigenvalues and eigenvectors, and this is our practice questions, and these practice questions are very important for your conceptual point of view, because when you solve it and by hand you have you will know more about all these concepts, and the basic definitions and terms we learn in this characteristic equation, link matrix, eigenvalues, eigenvectors, applications. Google page rank, and etc. These are the most important terms which we used in our today lecture. So this is the end of our lecture.